Okay, so this is your theory video for your Intro to Circuits lab. I'm really not going to be telling you a heck of a lot more than you should get through the reading, but maybe we can clarify a few things. So first is using resistor color codes to determine the resistance of a given resistor. So what you see here is a resistor. It's a 4-band resistor, so what that means is the first two are giving you the first two significant figures of the resistance. The third band is giving you the multiplier, what you multiply those first two figures by to get the total resistance. And then the fourth is known as the tolerance. What percentage plus or minus the resistance could actually turn out to be if you're using very specific values in a given circuit. You'd want to have a very small tolerance, meaning you'd want a very small percent difference, percent change compared to the value you would get from these first three. So here we go. The first band for this one here is blue. And so that tells you your first digit here is 6. Your second band is red. And you go back to the chart here. Red is 2. The third band is green. That's our multiplier. So that means over here, we look for our multiplier. It's 100,000. I'll write that all out. And it contains the units of resistance. And then the fourth, it might look yellow, but it's either gold or silver usually in terms of tolerance. Sorry, gold or silver. You can get some of these others, but those are very high specialty resistors. So the fourth band here is gold. And that's a tolerance of plus or minus 5%. So we would just call it 5%. And so then what you have now is 62 times 100,000. Or you could quickly get on a calculator just to check. And you get 6,200,000. So the resistance is 62 times 100,000 ohms. And so that's 6,200,000 ohm. And you could just use 6.2 mega ohm. $6.2 million ohms would be the way to look at it, with a 5% tolerance, meaning the value listed is not perfect, and so with a 5% tolerance, you could be 5% greater or 5% smaller than your 6.2 mega ohm or 6,200,000 ohm. So that's the basics of your resistor color codes. If you came across a 5-band resistor color code, then the first 3 bands would be significant figures, and then the 4th would be your multiplier, and then the 5th would be the tolerance. Most often you'll come upon 4 or 5 color bands on our resistors. Okay. Again, from the write-up, it hopefully should be clear how to measure voltages. So here I have my voltmeter. I've coded the positive electrode, the positive probe in red, the negative probe in black, and the idea is the positive probe is supposed to be touching the higher potential side of your circuit and the negative probe touching the lower potential side, and that will give you a positive voltage. So the idea here is that if this is the plus side and this is the minus side of your source, then theoretically positive charges are created up here. They come out of the source, and if these are ideal conductors for these wires, then all along here up to this point, this is the highest electric potential you're going to have. If your source is 20 volts, that means your positive charges up here have 20 volts of electric potential. When they jump through resistor 1, they decrease in their electric potential energy according to the voltage that we read across here. So if I want to read the voltage across this circuit element R1, I would attach my positive voltage probe to the more plus side of the resistor. That would be this side, it's nearest the positive, and this side is nearest the negative. And so whatever reading you get out of this, that will be the voltage drop from here to here. So let's say you're at 20 volts all up here, and this voltage drop was 12, then it would be 20 minus the 12, which would give you 8 volts of potential, electric potential at this point. Regardless, what you would read off this voltmeter is the voltage drop across R1, the electric potential energy change. Going through this resistor, the charges up here lose electric potential energy. To then measure the electric potential or the voltage across your second source, I will go ahead and connect my negative lead to the more negative side and my positive or red lead to the more positive side. And I have to specifically look directly across these 2 points on either side of the resistor. This potential will be a positive value, telling you how much the potential has dropped from here to here. What we should see is that the electric potential created by this, the voltage, again, let's say it's 20 volts. Let's say this was 12 volts, and it would be 20 minus 12. We'd have 8 volts potential difference here. And then from here to here, assuming this is now 0, 20 volts, 0, this would be your 8 volt change. And so everywhere along here, your chargers should have 0 electric potential or 0 potential energy. And so they need to go back into the source, get boosted up to higher potential, and run the circuit again. So this is measuring the voltage of just R2. And the idea is you need to bridge the circuit. If I went ahead and connected here, I should get the same potential drop across here, but it's going to be the sum of the 2 drops. And we'll see, we should expect that if this is a 20 volt source, meaning charges get boosted up to 20 volts here, and then down to 0 here, we should see 20 volts here. And it doesn't matter where I connect them, if I connect them here and here, etc. It's becoming a little messy. It looks like my probes are going across here, but the idea is any measurement from any point along here to any measurement across here, the voltage will always be the same. It'll equal the voltage of the source, but it'll also equal the total voltage drop across both resistors. And so you keep playing that game, you should see this voltage plus this voltage should equal the total source voltage. Okay, going on to currents. And I'm basically showing you the figure in our lab write-up. The ammeter has to be placed in the circuit. You have to cut the circuit at this point, insert the ammeter so that current flows through the ammeter as if it's its own circuit element. So here we'd be measuring the current coming out of the source, and that should be the same current throughout. Measuring the current coming out of R1, we would be breaking the circuit at this point and inserting the ammeter with its positive red lead here and its negative black lead here. That will measure the current coming out of this source. And then last, the current coming out of this resistor. To measure it, you would be placing the positive ammeter lead here and the negative ammeter lead here after cutting the circuit. What we should see is no matter where you measure the current, it's like a pipe of water. Water has to go sequentially or serially through R1, then R2, and back to the source. There's no way in which the current can leave. And so the current that leaves the source must equal the current that comes back in. And so what you should see in this setup is that the currents are all the same. Only when you have a break in the circuit, where you have a branch coming out, let's say, that branch will get a different current, and we have to remember that the current that goes into a branch equals the sum of the currents out of a branch. That ends your video.